Hello again everyone. So in this video I want to start looking at what happens if we disturb a chemical equilibrium. So our example for this says that Kp for the following reaction is 0.16 at 25 degrees Celsius, and then we're given a chemical equilibrium which has an enthalpy associated with it. We can see it is an endothermic reaction because it has a positive enthalpy. And then it says qualitatively predict the effect of the following changes on the position of the equilibrium. Alright, so the first question says, what happens if we remove some Br2 gas, some bromide gas? Alright. So of course, disturbances of chemical equilibria can be rationalized using Le Chatelier's principle, or in general using the reaction quotient in some manner. But because we just have to qualitatively predict, so we'll in general discuss it in terms of Le Chatelier's principle and the equilibrium itself. So how does removing some Br2 disturb this equilibrium? So of course, Br2 we can see is a product in this case, right? So Br2 is on the product side. So that means by removing that, we are reducing the product concentration. And we know that a system will respond by doing in other words, will want to respond in the opposite manner of whatever the disturbance was. So if we removed, the disturbance was to remove Br2, the system would want to increase the Br2 concentration again. Alright, and the only way that the system can increase the Br2 concentration is by favoring the forward reaction, and hence by reducing the reactant concentration and hence increasing the product concentration. Alright, and that means our equilibrium shifts to the right. So let's write down typically how I would write that down. It says, so what is our disturbance? So our disturbance is removing Br2 gas, which is a product. And this of course has the effect that therefore the system will respond by wanting to produce Br2 again, right? Which has the effect, if it wants to produce Br2, what does the system need to do? It therefore needs to decrease the concentration of NOBr, the reactant, right? It's our reactant. If it's reducing the reactant, it means it needs to favor the forward reaction. And it needs to favor the forward reaction to do what? To re-establish equilibrium. Okay, and then just to link to what the question says, qualitatively predict the effect on the following changes on the position of the equilibrium. We say then it shifts the equilibrium to the right. So meaning the equilibrium will disproportionately shift to the right to re-establish equilibrium. Okay? You can also technically see that in the reaction quotient. If you think about what the reaction quotient is, it's NO squared Br2 divided by NO Br squared. What did we do? Well, so when the system is at equilibrium, right, Q is equal to K, or Kp in this case. What we did is we decreased the bromine concentration. Decreasing the bromine concentration decreases our numerator. Decreasing the numerator in a value means that we change this from Q equals to Kp to Q being less than Kp. If Q is less than Kp, it means that for equilibrium to be re-established, the forward reaction must be favored for equilibrium to be re-established. Hence, it means exactly as we wrote there. The forward favors the forward reaction to re-establish equilibrium, and therefore it shifts the equilibrium to the right. Okay? Also known as Le Chatelier's principle. Okay? So that's A. So let's look at B. B now says, let me just wipe that. B says, what happens if we add more NOBr? Alright, so it's, in this case, what is our disturbance? Our disturbance is we add NOBr. So we add reactant. And in a similar manner, what would the system want to do? So the system would want to react. The system responds by wanting to reduce the NOBr. Right, and how does it then reduce the concentration of NOBr? It means the forward reaction must be favored again, right? We must favor the forward reaction. And if the forward reaction is favored, that means the equilibrium shifts to the right. You can also see it again in the reaction quotient. If you increase the concentration of NOBr in the reaction quotient, so let's start it again here. So at equilibrium, Q is equal to Kp. If you increase the concentration of NOBr, that means you've increased the denominator. That means Q's value will decrease, making it less than Kp. If Q is less than Kp, that means for equilibrium to re-establish, the forward reaction must be favored until Q equals Kp again, and hence the equilibrium will shift to the right until equilibrium is re-established. Alright, so you can see how Q gives us the same indication as the, let's call it qualitative prediction of Le Chatelier's principle. Right, let's look at C. C says, what will happen if we increase the temperature to the equilibrium position for this reaction? Now, this all is dependent then on the enthalpy. So the enthalpy here of reaction, so the standard enthalpy of reaction, delta R, reaction, enthalpy, the standard, that's what the zero is, in this case is larger than 0, right? Because it's positive, 16.3 kilojoule per mole reaction. So that implies that we can actually write our equilibrium as follows. NOBr gas. So if it's endothermic, right, so it's positive, the enthalpy is positive, that means our reaction requires heat to proceed. So heat we can model as a reactant of sorts. And then we form nitrous oxide plus bromide gas. All right. Because it's endothermic, it absorbs heat. The reaction absorbs heat to proceed. All right. Now, increasing the temperature has the same effect as adding heat. All right, so that's our disturbance in this case. Is increasing the temperature is the same as adding heat. So in principle, what have we added to the system? What's our disturbance? It's like we've added, so let's say it's like we've added a reactant, right? It's like we added a reactant. Because the reaction, when it's endothermic, requires heat to proceed. So as you can see, as we wrote it down there, if you increase the temperature, that is meaning you add heat to the system. And because the system or the reaction, when it's endothermic, absorbs heat, increasing the temperature means it absorbs more heat. All right. So what we've in principle done is this increasing of the temperature is similar to adding a reactant or increasing the concentration of a reactant. So it's similar to what happened in B. So in B we said the forward reaction is favored, and it's the same here. The forward reaction is again favored because we increased the amount of heat added in the system because we increased the temperature. All right, we added the stuff that the reaction needs to proceed in the forward direction. All right, and that's what we're looking at here. So this means the forward reaction is favored. And if the forward reaction is favored, that means our equilibrium shifts to the right. Okay. Think of it as the reaction, an endothermic reaction needs heat to proceed. So increasing the temperature will mean that you're actually giving the reaction what it needs to proceed. So that would mean that you are forcing the reaction in the forward direction. All right. Cool. Right, so let's move on to question D, which says, what happens if we decrease the container volume? Now, decreasing the container volume, in principle, increases the pressure. So, and I also want you to model this as follows. So think of it as 2NOBr. So right, that means we have 2 mole of NOBr gas in equilibrium with 2 mole of nitrous oxide gas plus 1 mole of bromide gas. So that means in equilibrium with 3 mole gas. And let's even just draw that. So it means for every 2 molecules of gas on the left, on the reactant side, we have 3 molecules of gas on the product side. I mean, they have identities, so we can make them colors like that. And like I said, decreasing the volume, so a decrease in the volume actually means we increase the pressure of these gases. So how does the system want to respond? Well, an increase in the pressure means the system wants to decrease the pressure. And how will it decrease the pressure? Which side of the equilibrium will be favored if it wants to decrease the pressure? Well, it's the side with the less number of mole of gas. So to decrease the pressure, the equilibrium needs to shift to the side that has only 2 molecules of gas instead of 3 molecules of gas, right? So by reducing the container size, we force the system to go into the side that only has 2 molecules of gas, right? Because 2 molecules of gas can occupy a smaller space more comfortably than 3 molecules of gas, right? Or 3 moles of gas. So therefore, the system shifts towards the side which has a lower number of important gas molecules. Gas molecules, gas moles, I mean, they're equivalent, right? So you count the number of mole of gas on either side, and if the pressure increases, the system wants to decrease the pressure. How does it do that? It shifts to the side towards which there's less number of mole of gas. So in this case, the system, or the equilibrium shifts to the left. All right. If we increased the volume and the pressure decreased, the system would of course wanted to do the opposite. It would have wanted to increase the pressure again, and hence it would have shifted to the side that had more gas molecules, in other words to the right. Okay, so that's what you need to remember. Alright, so volume is connected to the pressure, and that's how you judge that. Alright, so volume and pressure are connected. Temperature is connected to the enthalpy, and you model enthalpy as heat, and you need to figure out whether or not it's a reactant or a product, depending on whether or not your reaction is exo or endothermic. And then you can easily note if you're adding heat or removing heat, and then you can find that out. And concentrations are, you can either look at the reaction quotient or you can figure that out with the Chatelier's principle. Okay, so that's disturbances of chemical equilibria in a nutshell. I hope this was insightful, and I'll see you as always in the next video.